Thanks for joining us on our fifth lesson of Wave Sound and Light. Today we're going to be looking at longitudinal waves. Now before we will be able to see what the difference is in longitudinal waves, we first need to go back to what was transverse waves again. That was when the displacement of the wave was perpendicular to the movement. Now perpendicular refers to the fact that it was 90 degrees to the movement. So once again, here's an example of a transverse wave, and then we will see its rest position. That means the area here where the wave will have a zero disturbance indicates to us that the wave made its displacements perpendicular to the movement. Note though, the wave is moving, in this case forward, and the displacement of the wave is thus 90 degrees towards this movement. Now when we look at longitudinal waves, a best example is if you've got a slinky that you are then pushing back and forth. Now for those of you that hasn't seen a slinky before, it's basically a long piece of wound up metal that can actually then, when stretched out, you'll see the specific spirals as it is. Now what we're going to be doing is we're going to keep this one end of the spiral fixed, and we are going to, on the other side, take our hand and push this back and forth. Now this back and forth movement will cause some areas of the slinky to become compressed and some areas to be slightly more stretched out. And in order to explain longitudinal waves, we'll then see the definition as the displacement being parallel to the movement. Now note, the movement of the slinky is still forward, and the slinky also gets compressed forwards, and that means in our case these two lines are parallel to each other. So as said, the displacement of the wave in this case is parallel to the movement, because the movement is going forward, but so the displacement is also back and forth movement. Therefore the two is parallel. Now you would note that sometimes they indicate a slinky with just drawing in the lines without actually showing the spirals. Now once again, there's a difference between a pulse and a wave. A pulse meant to us a single disturbance. So for a longitudinal wave, it's a quick back and forth movement, only one of them. But when I'm going to have a repetition of this back and forth movements, then I'm going to produce a wave from that. Now as said previously, we've got areas then in this wave that there's going to be of the springs compressed and stretched out. Now we call the areas where these springs are compressed as compressions. And those areas of the spring that's slightly more stretched out is called rarefactions. Please take note of the spelling for our rarefactions here. Now waves are seen as a form of energy transfer. So it's a way of me transferring energy from one point to another. And in this case, by moving our hand back and forth here in the beginning, we transfer energy to these spirals. These spirals are getting compressed and moved further apart, and this is how it transfers the energy to the next spring and to the next spring until it eventually reaches the point of interest here. And this movement is then seen as compressions and rarefactions. Now the further these strings stretched out here in the rarefaction spot, the greater the amount of energy that's being transferred. So the stretching out part, that is displacement, are then seen as a way of measuring the amount of energy. Now we would like to go and determine wavelength. Now the definition for wavelength was again the distance between two consecutive points in phase. Now we would first need to go and establish again points that is in phase. And that again was the definition where the 2 points that move at the same position at the same time. Now let's go and apply this to a longitudinal wave. Now the points that we're going to be looking at is the points in the middle point of a compression. Right in the middle of my compressions, those are all my compression middle points. And the same goes for my rarefactions. Right in the middle of the rarefaction, that's also going to indicate to us the rarefaction points. Now these can be the 2 points that we're looking for. Remember, 2 points at the same distance at the same time. So for example, two compressions is 2 points at the same position at the same time. So is two rarefactions as well. Two positions at the same place at the same time. And note again, for a wavelength, this must be consecutive points. That means points that follow each other. So it can't be between your first point over here and the last point over there, because they are not consecutive. That means they're not following each other. So this can be seen as one wavelength, which is indicated by the symbol lambda, and the same happens here for 2 points that was in this case also part of my rarefactions. If they're consecutive, they can also be seen as a wavelength. And the last point which we can also mention is then once again 2 consecutive points for my compressions that can also be seen as a wavelength. Now the question which I would like you to go and attempt is to go and draw a longitudinal wave and indicate compressions, rarefactions and a wavelength on that wave pattern of yours. Remember to first pause your play and attempt this before you're going to look at the answer. Good, now I've decided to go and draw my wave, in this case as lines instead of the spirals. You could have still used the spirals, it would mean exactly the same thing. Now we're going to be looking for points in phase. So that means when I look at a compression, in the middle of a compression, I would find a point. So also for rarefactions, right in the middle of it will be the point. So two consecutive points in phase would be the distance in this case between my two rarefactions. That could indicate a wavelength. And also 2 points in phase when it comes to the compressions could also be seen as my wavelength indicated by lambda. Now in our next lesson we're going to be looking at key points on your longitudinal wave and how it can be compared to a transverse wave.